Hello. So based on several requests, I'd like to explore this question of finding a formula for the powers of a matrix. So to make this much more concrete, I'm going to introduce this particular 2 by 2 matrix. So before we start, some preliminary ideas and notions that we need in our computation. Recall that for every square matrix A and every invertible matrix P, the power P inverse A P to the n is equal to P inverse A P. So, in other words, finding powers of this form allows us to indirectly compute the powers of A to the n. Of course, whenever these two are available. So, the idea is to come up with a particular P that can do the work for us. So, if, for example, if P inverse A P is diagonal, then computing the powers of such matrix, it's just computing the powers of the diagonal. So that's what we're going to do. We're going to find a basis for the matrix A, if possible, that will make this particular matrix diagonal. Because that's exactly what this is indicating. This is just a change in coordinates. So let's find such change of coordinates. Okay. So first, I'm going to let A be the matrix 1, 1, negative 1, 1. From here, immediately, we can see that its characteristic polynomial, the determinant of A minus Ti, is nothing else but 1 minus T squared plus 1. So, the roots of this polynomial are lambda equal to 1 and plus minus I, where I is the imaginary complex number. So, imaginary unit. An easy verification of that fact can be just associated with introducing these numbers instead of this t. So just as a substitution. Now, let's explore each of the cases associated with this. So first, what happens when lambda is 1 plus I? So in this case, well, we need to find a description of the eigenspace associated with this eigenvalue. And well, to do that, we'll start like this. Let's find a basis for the null space associated with A minus 1 plus I times the identity. Well, such a matrix is the following: negative I, 1, negative 1, negative I. From here, we'll start a series of reductions, the first one being multiplying the first row by I, and thus obtaining 1, I, negative 1, negative I. Then just from here, we're going to add in the following way. And now obtain 1, I, 0, 0. So from this reduction, what we see is that a vector x1, x2 belongs to the eigenspace associated with this eigenvalue, if and only if x1 plus I x2 is equal to 0. But that is equivalent as to indicate that x1 is equal to negative I times x2. So this happens exactly when we can write x1 and x2 as negative I x2 x2, which of course we can describe as x2 times negative I 1. What does this mean? This means that the eigenspace associated with this eigenvalue is nothing else but the span of the set containing the vector negative I 1. Okay, so now we move to the next eigenvalue, which it's something that we have to remark. It is a conjugate of this one, right? Why? Because for every square matrix with real entries that has a complex eigenvalue, well, it also has its conjugate as one of its eigenvalues. That's one of the properties of the characteristic polynomial, right? Polynomials in general, roots of polynomials with real coefficients. Okay, so now let's explore the next one. Well, once again, we need to find a basis for the null space of A minus 1 minus I times the identity. But then, well, what will be this? Well, let's take a look. Such a matrix is the following. Let's make another one. That would be I 1, negative 1, I. Of course, we start with a series of reductions, just as the way that we did it. So I'm going to multiply the first row by negative I, and I will obtain 1, negative I, negative 1, I. Then from here, another reduction. So to row 2, I add row 1, and I will get 1, negative I, 0, 0. So let's interpret this. This means that for a vector x1, x2 to be in the eigenspace associated with 1 minus I, well, it's equivalent as to have that x1 minus I x2 is equal to 0. In other words, x1 is equal to I x2. Equivalently, we have that x1, x2 as a vector is written as I x2, x2, which is, of course, x2 times I1. What does this mean? That means that we can express all the vectors in this eigenspace as linear combinations of elements from this collection. Well, something that we have to notice is that now, when we combine this vector with this one to form a basis, right? And we have negative I, 1, comma, I, 1. This one forms a basis over the complex numbers for C2. Okay? So that means that if we construct a 2 by 2 matrix with these two column vectors, we will get an invertible matrix over the complex numbers. And that's what we're going to do. So we're going to apply the same ideas that we had implemented in the past for finding inverses by adjoining to the matrix formed by these two columns, the identity matrix, and then performing row reduction until we get the unique row reduced echelon form. So for this, what I will do is I exchange the two rows, and now I have 1, 1, negative I, 0, 1, 1, 0. Then from this, I'll indicate to row number 2, I add I times row number 1. And I have 1, 1, 0, 2I, 0, 1, 1I. Then we'll continue with reductions. So now I'm going to multiply the second row by negative 1/2 I, and thus obtaining this matrix 1, 1, 0, 1, 0, 1, negative 1/2 I, 1/2. Then from this, one more reduction. We have to row 1, we subtract row 2, and we'll get this 1, 0, 0, 1, 1/2 I, 1/2, negative 1/2 I, 1/2. Right? So the matrix that is located here is the inverse. So now we're going to let P be equal to the matrix negative I, 1, 1. So its inverse is going to be, well, 1/2 of I, 1, negative 1, 1. Now, something to observe is that the matrix that we see here and the matrix that we see here, well, they're related to the transpose. Well, nice observation. Now, let's compute the product. P inverse A P. Okay, let's see. So this becomes 1/2 times I, negative I, 1, 1, times 1, 1, negative 1, 1, times negative I, 1, 1. Well, let's develop this. This is 1/2 times I minus 1, I plus 1, negative I, negative 1, negative I plus 1, times negative I, 1, 1. which now we may reduce to 1/2 times 2i plus 2, 0, 0, negative 2i plus 2, and then in its simplified form, 1 plus I, 0, 0, 1 minus I. Now look, these are exactly the eigenvalues associated with this matrix. So now the question is, well, how do we compute this product? Right? How do we compute this power, the power of this matrix? Well, so this results into the next portion of the exercise, which is, well, let's compute 1 plus I to the power of n. That's the fourth part. Well, to do that, let me do the following, because I think that we need to gain access to this at some point. And well, what is this? What is this number? You may say, well, look, one of the things that we can do is to write 1 plus I in its polar form. So, to do it, observe the following configuration in the imaginary plane. So if I indicate this is the real part and this is the imaginary part, you will see that this number corresponds to a vector on this plane, right? In the point 1 plus I. Well, look, the length of the vector that is associated here is the square root of 2, as each of these sides are 1. This is a right triangle, so this angle has to be 45 degrees. In other words, pi over 4. So we may write this in the following way. This is the square root of 2 times the cosine of pi over 4 plus I times the sine of pi over 4. Okay, so from this point, I think we now have the following. Because if you want to write 1 plus I to the power of n, we simply compute this. But then from here, we just distribute, we have the square root of 2 to the power of n, and by the Moi's formula, this becomes the cosine of pi n over 4 plus I sine pi n over 4. For those who would like to investigate on this idea. Well, why is that this might become useful? Well, just bear with me, because now we're ready to establish some conditions. 5. Recall that we know that P inverse A to the power of n, P, is equal to P inverse A P to the power of n. So we're going to set B to be P inverse A P. then we have that b to the n is equal to p inverse a to the n p, which is the same as to indicate that p b to the n p inverse is equal to a to the n. That's what I mentioned at the beginning, that we can compute this indirectly. Well, so let's proceed, right? So what is a to the n? So a to the n is going to be given by the following: negative I, 1, 1 times 1 plus I to the power of n, 0, 0, 1 minus I to the power of n. Remember, powers of diagonals are just computed by finding powers in the main diagonal. So times 1/2 of I1 negative I1. And well, we'll expand this to become this one. So now this is negative I, 1 plus I to the power of n, I times 1 minus I to the power of n, times 1 plus I to the power of n, times 1 minus I to the power of n, times, in matrix, negative I, 1, which now we express in this fashion: 1/2 of 1 plus I to the power of n plus 1 minus I to the power of n, negative I times 1 plus I to the power of n plus I times 1 minus I to the power of n. I times 1 plus I to the power of n minus I times 1 minus I to the power of n. And then on this entry, 1 plus I to the power of n plus 1 plus I minus I to the power of n. And well, it turns out that this has to be a matrix with real entries. So this is what I'm going to do now. From here, I'm going to let z be 1 plus I. So that means that the conjugate is exactly that. Right? Now, so whenever we have this structure, what we have is the following. This is 1/2 of c to the n plus the conjugate of z to the n. Factor in I, we have c to the n minus c to the n in this fashion, and then I times c to the n minus c to the n in conjugate, and then on this one we have c to the n plus the conjugate to the n. But look, we know that when you multiply two complex numbers and you compute the conjugate, that is the same as if you calculate the conjugates individually and then you multiply. So, what does this mean? That means that we can do the following reduction. This becomes 1/2 of twice the real part of c to the n. This one becomes 2 times the imaginary part of c to the n. This one is negative twice the imaginary part of c to the n. Well, this entry that we have right here is 2 times the real part of c to the n. And well, we may simplify this to the following: the real part of c to the n, negative the imaginary part of c to the n, the imaginary part of c to the n, and the real part of c to the n. Well, luckily, we already compute c to the n. So all that we need to do is to perform some extractions. So this has to be the following matrix: a square root of 2 to the n of the cosine of pi n over 4. This one is going to be the square root of 2 to the n sine pi n over 4. This entry, negative square root of 2 to the n sine pi n over 4. And lastly, square root of 2 to the n cosine of pi n over 4. And well, with this we finish. I hope that you enjoy it. Take care.